Hi and welcome. So today we're going to talk about section 12.2 and the topic is U substitution. Now last class we talked about section 12.4, which is applications of antiderivatives and applications of integrals, indefinite integrals in particular. And we talked about how marginal revenue, marginal cost, or maybe even marginal profit, but mostly if we're given marginal revenue or marginal cost, then we can go backwards, we can find the antiderivative and come up with the original cost function or the original revenue function. And we looked at some examples, and I want to start with an example similar to ones that we talked about in our last class. In this example, we have marginal cost for a company producing X units of a product is marginal cost, MC, is equal to 60 times the square root of 2x plus 1. And fixed costs are $340. And we want to find the total cost function. Okay, so last class I reminded you about how marginal cost is the same thing as the derivative of cost. So if we want to find the original cost function, C of x, that means that we want to find the antiderivative of marginal cost. So we want to find the antiderivative of 60 times the square root of 2x plus 1 dx. Okay, so the long stretched out s and the dx at the end say find the antiderivative of the thing in the middle. Now, I know when I find an antiderivative, also when I find derivatives, but when I find antiderivatives, anytime that I see a root, I want to turn that into a power, and my power is going to be a power of 1/2. So we have the integral of 60 times 2x plus 1 raised to the 1/2 dx. Cool. Okay, so I'm thinking I'm ready to find an antiderivative, and the rules that I know are if I have a number sitting by itself, then its antiderivative says write down that number and tack on an x. We don't have that situation here. This 60 is times this 2x plus 1 raised to the 1/2, so the 60 is not sitting by itself. The other rule that we have is if we have x raised to a power, we add 1 to the power and divide by that new power. Now here, what we have is fancy stuff. This 2x plus 1 is being raised to a power. And what this kind of reminds me of is this part of our function kind of reminds me of the derivative rule of the chain rule, the one that says take the derivative of the outside, keeping the inside the same, times the derivative of the inside. In other words, when we have fancy stuff raised to a power, then I'm kind of thinking of our chain rule when we're talking about derivatives. So we're actually going to have sort of an antiderivative rule for functions that have an inside in them. And so we actually can't go forward with this at the moment. We're going to have to put this problem on hold because we need to learn a new technique for finding antiderivatives of functions where we have a fancy inside. So we're going to put this problem on pause, and I want to talk to you about this technique called U substitution. Okay. So the tool that we're going to talk about is a tool for evaluating integrals with, and I'm going to call them fancy insides. So in this integral over here, I have a fancy inside. The fancy part is the 2x plus 1, and that's inside of the parentheses, and the parentheses are raising this 2x plus 1 to the 1/2. Okay, so that's our technique, and that's what section 12.2 is all about. Our textbook calls this the substitution rule. I like to call it U substitution, or U subs. Okay. So at this point, before we start talking about this technique, I want to look at an example from earlier on in the semester. So let's say that we have y equals 3x to the 5th minus 7x raised to the 10th, and we want to find the derivative. Now, if we were in class right now, I'd ask you to turn to your neighbor and say hi, and then tell your neighbor how to find this derivative. And hopefully what you would tell them is you would say, oh, I see that this is a fancy function being raised to a power. So I have an inside function and an outside function, and I need to apply the chain rule. And so the chain rule says take the derivative of the outside, keeping the inside the same, times the derivative of the inside. Okay, so derivative of the outside, my outside function is u to the 10th. So the derivative of the outside is bring that 10 down, keep the inside the same, now raised to the 9th, so that's our derivative of the outside, keeping the inside the same, times the derivative of the inside, and the derivative of the inside is 15x squared, so I bring the 5 down, 3 times 5 is 15, x to the 4th minus 7. Okay, so there is our derivative. Okay. Now, if you're like, oh crud, I haven't thought about derivatives in a while, and I haven't thought about the chain rule in a while, you might want to go back and review the chain rule a little bit. Okay, so that's the chain rule, an example of using the chain rule to find a derivative. Okay, so here's a new problem. We would like to evaluate the integral. And our integral is the integral of 10 times 3x to the 5th minus 7x raised to the 9th times 15x to the 4th minus 7 dx. Whew. All right, we want to evaluate this integral. Now you might be thinking to yourself, oh, no problem. I can just find the antiderivative of all these things in the middle, and the answer is no, you can't do that. And here's why. You are not allowed to just take antiderivatives here because there's multiplication going on. There is a power on the outside of these parentheses. So just looking at this thing is a mess. We cannot just look at it and take antiderivatives by using the antiderivative power rule. Okay, so let's think about what this integral sign says. The integral and the dx say the function in the middle is a derivative, and the question is, what was the original function? If only we knew a derivative that looked like this, then we might know what the original function was. If only we knew a derivative that looked like the thing between the integral sign and the dx, then we might know what the original function was. Oh, look, check this out. This derivative right here is exactly the expression that's in our integral. So because of that, this derivative came from 3x to the 5th minus 7x raised to the 10th. So our antiderivative of all this stuff is 3x to the 5th minus 7x all raised to the 10th. Oh, I also need to add on a plus c because maybe there was a constant on the original function that when we took the derivative it went away. Awesome, great. So if you happen to start to watch the video and then you pause it after doing this chain rule practice problem, and then you happen to go out on your walk, which, you know, if you have a pet, you can go take your pet on a walk, and out on the street you see this integral that some child or somebody has drawn on the sidewalk when you're out on your walk, and And you look at this and you say, oh, I just happened to have taken the derivative of a function and that's what I got. So I know what the original function was. Awesome. That is, okay, honestly, that's not really a good way to find antiderivatives, but if you're lucky, it does work that way. Okay. Now, in reality, if you're given some kind of a complex integral like this one right here, we want to have some kind of a technique that will help us find our antiderivative. We cannot depend on somebody who's done an example on the other board that exactly matches what we're looking for. So what I'm going to walk us through is how do we find this answer? How do we find this antiderivative by using this technique of U substitution? So U substitution is our new integration technique. Okay, so in this first example, which is the one where we already know the answer, I'm going to walk through the steps and I'm going to write down the steps over on the side. And what I want you to do is I want you to watch what's going on for this first example and hold off on your thoughts and questions of why are we doing this process, and we'll see kind of how the pieces all fit together in the end. Okay, so in our first example we have the integral of 10 times 3x to the 5th minus 7x raised to the 9th times 15x to the 4th minus 7 dx. And so when I start to see a bunch of fancy things all multiplied together, maybe fancy things raised to powers, my thought is maybe I should try this new technique of U substitution. And the first step in doing a U substitution is to choose U. So we are going, in our case, we are going to choose our U value to be the part inside the parentheses that's being raised to the power of 9. So we're going to choose U to be 3x to the 5th minus 7x. And that choice is important, so I'm gonna circle it. Now, as a rule of thumb, and I call this a rule of thumb because it usually works pretty well, but it doesn't work 100% of the time. As a rule of thumb for how to choose the value for U, one way to do that is to look for the most complicated part of this expression, this function that we have here. In this case, that's the 3x to the 5th minus 7x raised to the 9th. I would think of this as the most complicated part. And then I want to choose the inside to be my U value. So our rule of thumb is to look for the most complicated part of the integrand. Remember, the integrand is the stuff between the integral sign and the dx. So look for the most complicated part of the integrand and choose the inside of that inside of that complicated part. Choose the inside as your U. So in this case, we chose U to be 3x to the 5th minus 7x. That is step 1. Okay, step 2, once I have chosen my U, and what I might do is I might write this U value down off to the side. So my U is 3x to the 5th minus 7x. I've circled it because it's important and I'm going to need to come back to it. Step 2 is to take the derivative of U. So the derivative of 3x to the 5th is 15x to the 4th, and then the derivative of 7x is 7. So I have 15x to the 4th minus 7. And I can call this U prime, but what I'm going to choose is I'm going to choose to use that Leibniz notation that we talked about. Like when we talked about Leibniz notation, it was dy over dx. Because this is U, this will be du over dx. So our derivative, du over dx, is 15x to the 4th minus 7. Okay, So that is step 2. Step 3 is to solve this equation for dx, which is in the denominator of this fraction. Okay, so to solve this equation for dx, the first thing I need to do is get that dx out of the denominator. So I'm going to multiply both sides of the equation by dx. On the left side, the dx's cancel, and I'm left with du equals 15x to the 4th minus 7 dx. Okay, so I'm still trying to solve for dx. Dx is out of the denominator, but to get it by itself, I now need to divide both sides by 15x to the 4th minus 7. All right, that leaves me with, on the right side, dx, and on the left side, I'm left with du over 15x to the 4th minus 7. So I have now solved this equation for dx. Okay, so that is step 3. Step 4, we are going to make some substitutions. So step 4, we will make some substitutions for u and dx. Okay, so our original problem is the integral of 10 times 3x to the 5th minus 7x raised to the 9th times 15x to the 4th minus 7 dx. Step 4 is to make some substitutions. The first substitution that I'm going to make is our choice for u. So u was 3x to the 5th minus 7x. I'm going to get rid of the 3x to the 5th minus 7x and replace that with a u. So we have the integral of 10 times u to the 9th. I've replaced that fancy stuff with a u, times 15x to the 4th minus 7. And now I'm going to replace this dx at the end with the thing that we solved over here. So we saw that dx was equal to du over 15x to the 4th minus 7. So I'm going to replace that dx with du over 15x to the 4th minus 7. Okay, so after we made these substitutions, we substituted in for u, and we replaced dx with du over 15x to the 4th minus 7, then the next thing we want to do is try and clean this up. So when I look at what's going on here, I see a 15x to the 4th minus 7 in the denominator, and one that's part of the numerator as well, which means that these guys can cancel. And what that leaves us with is the integral of 10 u to the 9th du. So step 5 is to cancel and simplify. All right, now that we have everything in terms of the variable u, now that we have no more x's left here whatsoever, then our next step, step 6, is going to be to find the antiderivative. Okay, so step 6 is to find the antiderivative. Now, when I look at this integral, this guy is way easier to deal with than this crazy complicated function I have up above. In fact, 10u to the 9th, to find my antiderivative, that's not so hard. To find this antiderivative, I'm going to add 1 to the power. So I have u to the 10th, and I divide the number in front by that new power. Okay, so I have 10 over 10 u to the 10th plus c and 10 over 10 is 1, so I can write a 1 or I can just leave it blank. And I have u to the 10th plus c. So we just found our antiderivative, and our final step in this whole process, step 7, is to substitute back in for our u value. So in our case, we have u to the 10th. Our choice for u, and I'm glad that I circled it so I could find it again, my choice for u was 3x to the 5th minus 7x. So down here, instead of a u, I have 3x to the 5th minus 7x raised to the 10th plus c. So all the work that we've done here, this work off to the side of choosing a u, taking a derivative, solving for dx, making substitutions into our integral, canceling, getting an integral entirely in terms of u. All of that work was the u substitution. Now we take an antiderivative. After we do the antiderivative, we plug back in our choice for u. And so we do end up with our final answer. Now, it feels like a lot of steps because maybe this is the first time that you've ever seen this idea. But we're going to do a few more examples of these, and as you work more examples, then these steps will flow a little bit better. Okay, so in our next section, we're going to do a couple of examples, and then in our final part of our lecture today, we're going to go back and revisit that first example of the marginal cost example. Okay, thanks.